The Pantheon dome built 125 Common Era remains structurally intact after 2,000 years. Modern Portland cement concrete fails within 50 years when exposed to seawater and salt spray conditions. Roman concrete strengthens in seawater while modern Portland cement concrete deteriorates and fails relatively quickly. The recipe that Rome used to build structures that outlast modern materials was documented but then forgotten. Vitruvius, the Roman architect, described the exact formula in his treatise De Architectura in precise detail. Pliny the Elder confirmed that seawater-based concrete grew harder over centuries rather than weakening significantly. This knowledge disappeared completely after Rome declined and remained lost for 1,500 years until now. Joseph Aspdin reinvented Portland cement in 1824, but it was fundamentally inferior to Roman formula. Engineering history celebrates Portland cement as progress, while ignoring 2,000 years of superior Roman concrete. Portus Cosanus Harbor proves Roman concrete superiority by remaining structurally perfect after 2,000 years. Ancient structures speak louder than modern theories about which concrete formula actually achieves permanent durability. Vitruvius served Augustus and wrote specifications that builders could follow and replicate across the entire empire. Pliny recorded specific observations of structures he had personally examined that proved seawater improved concrete. Pozzuoli in Campania near Naples contains volcanic ash pozzolana that was systematically harvested for concrete. Pozzolana volcanic ash contains silica and aluminum compounds that react with lime in seawater solutions. Seawater contains magnesium and other minerals that trigger specific chemical reactions that Roman engineers deliberately exploited. Slaked lime was prepared by burning limestone and mixing with water, creating a reactive base material. Augustus directed massive construction projects that required reliable concrete formula for successful long-term infrastructure development. Roman engineers systematically sourced pozzolana from specific quarries near Pozzuoli for maximum quality control purposes. Vitruvius documented the sourcing process and proportions so builders throughout the empire could replicate success. Portus Cosanus concrete structures remained perfectly preserved underwater because seawater triggered beneficial strengthening chemical mechanisms. Unlike modern Portland cement, Roman concrete actually improved when constantly exposed to saltwater immersion conditions. 20th century harbors built with Portland cement began failing within decades, requiring constant, expensive repairs throughout. Joseph Aspdin's Portland cement was inferior in marine conditions but superior in manufacturing consistency and scalability. After Rome declined, the pozzolana sourcing knowledge and mixing procedures disappeared from European building practice. Medieval builders had access to Vitruvius texts but lacked the organizational capacity to source pozzolana systematically. Renaissance engineers studied Vitruvius but could not reconstruct the formula without volcanic ash and seawater chemistry. In 1824, Joseph Aspdin created Portland cement as an industrial solution for mass production. Portland cement could be manufactured anywhere, stored indefinitely, and transported globally, unlike site-specific pozzolana sourcing. Portland cement's fatal flaw only emerged decades later when structures exposed to salt water began corroding and failing. 20th century concrete harbors, dams, and coastal structures all began failing within 50 years of construction. In 2017, Marie Jackson at UC Berkeley published research explaining the chemical mechanism. Jackson identified aluminous tobermorite crystals forming inside Roman concrete, strengthening it progressively over many centuries. Seawater percolating through Roman concrete triggered tobermorite crystal growth that filled fractures and increased density. Portland cement experiences corrosion and expansion in seawater, while Roman concrete experiences strengthening and densification. Portus Cosanus concrete underwater for 2,000 years became stronger instead of weaker, proving Pliny correct. Jackson's research vindicated Pliny the Elder's ancient observations that Roman concrete grew harder in seawater. Jackson published her findings in the American Mineralogist Journal, providing thorough, peer-reviewed scientific documentation completely. Tobermorite crystals have a specific atomic structure that allows them to fill microfractures and bond with surrounding matrix. Seawater contains magnesium ions that enable the tobermorite crystal growth mechanism inside Roman concrete completely. As Roman concrete ages and tiny fractures form from stress and weathering, tobermorite crystals fill them automatically. The crystal growth increases concrete density significantly, making it harder and more resistant to penetration. Pliny the Elder described this exact phenomenon in the 1st century Common Era without understanding its chemistry. Vitruvius's specifications for pozzolana, seawater, and lime proportions perfectly match what modern chemistry proves optimal. Jackson's comprehensive methodology combined archaeology, chemistry, and microscopy to thoroughly reconstruct the ancient chemical mechanism. Roman concrete was designed to strengthen over time, while modern concrete was designed for immediate strength only. Roman engineers optimized for centuries of durability, while modern engineers optimized for manufacturing consistency instead. Modern material science ignored evidence that natural volcanic ash outperforms synthetic Portland cement in marine environments. Jackson's research proved that Roman concrete formula could be reconstructed from historical texts and archaeological analysis. The modern concrete industry constructed a narrative that Portland cement represented progress over all previous materials. Portland cement's global manufacturing and distribution advantages made it commercially dominant, despite its inferior performance. When Rome declined, the systematic organization required to source pozzolana was lost, making Vitruvius's formula irreproducible. Joseph Aspdin's Portland cement succeeded not because it was superior, but because factories could scale production globally. Academic engineering literature celebrated Portland cement as modern progress while dismissing Roman concrete as ancient. Billions of dollars invested in Portland cement infrastructure created institutional resistance to acknowledging superior alternatives. 2,000 years of physical evidence that Roman concrete outperforms modern materials was categorized as archaeology, not engineering. Roman formula required craft knowledge of pozzolana quarrying and seawater chemistry that did not survive Rome's decline. Jackson's American mineralogist paper presented electron microscopy data showing actual tobermorite crystals inside ancient concrete. The tobermorite crystalline growth mechanism creates stronger concrete over centuries of saltwater exposure, exactly as Pliny described. Modern analytical chemistry proves that seawater chemical composition triggers precisely the reaction Romans deliberately engineered. Portland cement experiences destructive expansion in seawater because its chemistry reacts differently with magnesium ions. Pliny the Elder's 1st century observation that seawater improved Roman concrete is now proven exactly correct. Modern coastal infrastructure could be designed using Roman formula to achieve durability instead of constant maintenance. Jackson's research shows Roman formula can be reconstructed using historical sources and modern material science. Pozzuoli volcanic ash remains available today, and seawater is abundant, making Roman formula reproducible immediately. The only barrier to using Roman concrete today is institutional preference for Portland cement, despite proven inferiority. The Pantheon dome, built 125 Common Era under Hadrian, stands as permanent physical proof. The Pantheon remains stronger than any modern concrete structure built 50 years ago in comparable marine conditions. Portus Cosanus Harbor sits intact underwater after 2,000 years because Roman engineers solved saltwater degradation. A superior building material was forgotten for 1,500 years, while inferior technology was refined and celebrated. Rome lost systematic knowledge of pozzolana sourcing, seawater chemistry, and craft techniques required for eternal concrete. Joseph Aspdin's Portland cement succeeded not because it was superior, but because factories could scale production globally. Modern concrete structures require endless repairs and replacement because Portland cement fails in marine environments. Marie Jackson's 2017 research recovered knowledge that was lost for 1,500 years. Jackson's peer-reviewed research vindicated both Vitruvius and Pliny as accurate observers of material science principles. Roman concrete formula can now be recovered, understood, and implemented using both ancient texts and modern chemistry. Vitruvius of the 1st century before Common Era described precise specifications that modern analysis proves completely optimal. Pliny the Elder documented observations of seawater-strengthened concrete that modern microscopy has now proven completely. The Pantheon dome under Hadrian demonstrates that Roman concrete achieves genuine permanence, unlike modern materials. Portus Cosanus underwater for 2,000 years proves that seawater actually strengthened Roman concrete progressively. Pozzolana volcanic ash from Pozzuoli was essential to Roman durability and cannot be replaced by Portland cement. Tobermorite crystal growth triggered by seawater transforms Roman concrete into stronger material over centuries progressively. Marie Jackson proved scientifically what Pliny observed in the 1st century, recovering lost knowledge through modern analysis. Vitruvius documented Roman concrete formula with precision that modern engineering confirms was completely accurate throughout. Rome created eternal concrete material, then lost the knowledge for 1,500 years until geologists recovered it. Hadrian commissioned the Pantheon dome in 125 Common Era, and it remains largest. Modern engineering now realizes that Rome solved concrete durability problem completely while modernity reinvented inferior solution. The recipe Rome lost can now be rebuilt using Vitruvius text, Pliny documentation, and Jackson's scientific methodology. Future buildings could achieve Pantheon-level durability using recovered Roman formula instead of constantly failing Portland cement. 2,000 years of physical evidence stands in Rome and underwater proving the formula works.